This is FRM Part 2, Book 1, Market Risk Measurement and Management, and the chapter on Value at Risk Mapping. Just a quick reminder, we spent some good time in the last couple of chapters taking a look at what's going on in that left tail, right? How do we figure out what's going on in that left tail? Now we're going to try to identify some risk factors so that we can map that ultimate value at risk estimate that we derive from all the different ways that we can consider value at risk. So just by way of introduction, let's suppose that we have a fixed income portfolio, and let's make this as complex as we can. Let's suppose that we have a portfolio that consists of some treasury bonds, some investment grade corporate bonds, some speculative grade corporate bonds, some mortgage-backed securities, some sovereign bonds, some supranational bonds. Let's even suppose that we made some loans to our neighbors. So we have all these bonds and loans out there. And let's suppose that this is worth, $500 million. And so what are we worried about? We're worried about essentially interest rates rising or other types of risk rising, and then the value of our portfolio falls, right? So what kind of variables are we worried about? Oh my gosh, let's think about all these things. We need to worry about what the central banks are doing. We need to worry about inflation. We need to worry about probability of default. We need to worry about exchange rates. We need to worry. I mean, I could sit here for 20 minutes listing all of the variables that we would have to worry about that will affect the value of our portfolio. But wouldn't it be awesome if we could collect in buckets some of these variables and identify a risk factor that summarizes those variables? And that's what we're doing here. So instead of having all this stuff related to, let's say, central bank behavior and inflation and exchange rates, let's suppose that we have one risk factor that summarizes those things and another risk factor that summarizes a bunch of other things. And so instead of 1 million variables out there, maybe we have 5 risk factors. So this makes our life easy. So this is really what value at risk mapping is. Let's look at those learning outcomes here. The first thing that I want you to pay attention to is those action words. Explain and summarize and differentiate and describe. None of those sounds like estimate or calculate or compute. And we're going to do some good math in these slide decks. And what I'm suggesting is that you follow along the math, pay attention to the details, so that if you're asked a question about doing the math, you can do it. But understanding the mathematics of this mapping is going to help you explain and differentiate and all those kinds of things. So look at this. Really, these learning outcomes are really based around what I just described: value at risk mapping, the process, the general and specific risks. We'll talk about William Sharpe a little bit. 3 methods of mapping portfolios. And then summarize. That's going to be the map, the math behind this stuff. Then we'll do a quick slide on a performance benchmark, and then we'll end with the conversation on some derivatives. All right. So I love this illustration here as part of a definition of value at risk mapping. And so look at the value at risk, and they have all the roots growing downward and outwards and sideways and backwards and forwards, and some are deep and some are shallow. Think of all those roots as those 1 million variables that I described earlier. But notice we have here a root cause H, a root cause K, a root cause Y, and then some minor causes as well. And so what we're really trying to do, notice that second block point. A complex portfolio can be broken down into its constituent elements that determine its value. So we're going to worry about those factors, those root causes that summarize all of those variables. I think the chapter tells us gives us 4 answers for this question: why is mapping so important? Boy, it's necessary when you don't have sufficient data on the positions. That makes perfect sense. It really reduces our effort in terms of evaluating the relationship between and among all of these variables. Just a quick example. I know I've said this to you in previous chapters. If you have a 100 stock portfolio and you're trying to compute the correlation coefficients between and among all those 100 stocks, remember, you have the correlation between 1 and 2 and 1 and 3 and 1 and 80 and 1 and 90 and 2 and 4 and 3 and 8 and all those. How do you sum those? Well, really, you got to take 100 times 99. So there are 9,900 of these correlation coefficients. Now, of course, divide by 2 because one varies with the other and the other one varies with the first one. And so notice in bolded in the bottom there, we've got this gigantic matrix. What did I say? 9,900. What do we squeeze it down to is some more manageable level to avoid computational problems. I just showed my students in the investments class this week how to do the Harry Markowitz efficient frontier. And we got this big old matrix in Excel going, but it's still manageable. Avoid rank correlation problems. I mean, you think about a fixed income portfolio. If you have a handful of Treasury securities, I mean, what's the Treasury securities correlation coefficient between and among other Treasury securities? I mean, they're probably going to be pretty close to 1. And so how do you rank these things? If you have one correlation 0.993 versus 0.994, I mean, of course, mathematically, those are not the same numbers, but practically, they probably are pretty close to it. And then notice the fourth one, reduces the time needed to carry out risk assessment and related calculations. So we gotta have a trade-off here between our desire to make a decision in the relatively and a reasonable amount of time versus our need to make a decision that incorporates all of the relevant risk factors. And so this is a classic marginal cost, marginal benefit analysis. Thank heavens we paid attention in microeconomics class. All right, how about some principles underlying the mapping? All right, what this mapping is going to do is help us to aggregate the risk factors. It's useful in measuring changes over time. And of course, it's really helpful when historical data is not available. So let's get started on this process here. So what we're going to do is marking to market. We always want to do that. Of course, we want to find out what that current value is. And then identify these common risk factors. So let's go back to my example with this fixed income portfolio. What are probably some common risk factors? Well, duration surely should come to mind, and we'll talk about that as we go through the slides. Default risk, that ought to be an element for at least most of those. I think I threw a treasury bill in there, 1 or 2 treasury bills. Then we bought some other sovereign bonds and some supranational bonds. So we've got to worry about currency risk. So there's a good example, duration, credit risk, and currency risk. So those are common factors that can be applied throughout the portfolio. So we're going to allocate that market value to each risk factor, and this is a good illustration here. So if we have 5 positions and 3 risk factors, notice that most of the positions are exposed to just 2 risk factors. So look at the market value of position 1. That's exposed to risk factor 1 and risk factor 2, but not risk factor 3. And then look at position 4, that's exposed to just risk factor 3. Maybe that position 4 is the treasury, and all we really need to worry about is duration. We don't really need to worry about, if we're a U.S. investor, we don't need to worry about currency risk, and we don't need to worry about credit risk. So we have these risk factors, and then notice the red arrows go down to the bottom. They kind of flow into that final risk aggregation bucket. We're going to construct a risk factor distribution. I'll show you a table here, and then I'll have an Excel spreadsheet to illustrate that. And then we're going to do some summing. Now, this table was taken directly out of the chapter, and this is a little bit more simple than it looks. If you go down the left-hand column, there are 5 positions. There's the market value after we mark to market of our 5 positions, and then that MV at the bottom is the total market value. And then there are risk factors, factor 1, factor 2, and factor 3. And then that kind of looks like a correlation coefficient matrix. Kind of looks like it. And then we're just going to do some summing. at the bottom. So we really have risk factor 1. So X1, X2, and X3 are going to be, just go into that matrix there and then imagine we're reaching out and trying to capture that market value. How much does the risk factor affect our market value? The answer could be 0, right? All those X11s and X42s, they could be 0. And what we could say is, no matter what happens, the market value of our portfolio is going to stay the same. That's not realistic, but that extreme example illustrates what those factors are. So those factors could be very low or they could be very high. Now let's take just a step back and revert to our very introductory investment days when we started with Harry Markowitz with the efficient frontier, and then William Sharpe developed that capital asset pricing model. And then we learned that total risk of a portfolio can be divided into 2 components, right? And this is how I learned it back in my graduate school days. Systematic risk and unsystematic risk. Of course, systematic risk was sensitivity to economic risks, the risks of the economic system. And then unsystematic risk is the risk that is unique or specific to that one particular financial security. Now, of course, this William Sharpe's diagonal model uses just a little bit of kind of different terminology, but the application is really just the same. So our model decomposes these returns into a common index component, maybe like the S&P 500 index for a stock portfolio, or maybe a Morgan Stanley bond portfolio index. And then an idiosyncratic component, which refers to the uniqueness, the specific risk of that particular asset and how it relates to everyone else. So really what happens then is that as more and more positions are added to the portfolio, right? More stocks or more bonds or just more positions added to the portfolio, the idiosyncratic component kind of goes away. In the academic world, we say that systematic risk or idiosyncratic risk virtually disappears. But as it applies to this value at risk mapping, it's still going to remain. So notice what I have. The latter disappears as more and more positions are added, leaving the common index component as the main driver of risk. So we're going to try to capture the main drivers of risk to go back to explaining value at risk. Now, the next question is, what did I say earlier? We had 5 risk factors. Wow, wouldn't it be awesome if some Nobel Prize winning economist came up with the optimal number of risk factors is 6. Then you could just say, well, the Nobel Prize, these people are really smart, let's just get 6. But of course, it doesn't work that way. What do we want? We'd like to have 1 or 2 because that's easy to work with. It's convenient, but then it might not capture some of those important risks. So more risk factors sounds more efficient than fewer risk factors, but then where do you truncate? Where do you hit the ceiling? Is if 4 is better than 2, then 6 is better than 4, then 10 is better. So when you keep adding, then you got to think, oh my gosh, what am I doing? Am I adding value as I add another risk factor? So once again, notice I have in bold, an appropriate trade-off, marginal cost, marginal benefit. So what are we doing? Quality of approximation versus faster processing. Now, the choice and number of these general risk factors will directly affect the size of those specific risks. And so let's go back to my example that I talked about just a few slides ago. Look at that first block point. Bonds, we have a portfolio, bonds with different maturities, different ratings, different terms, and different denominations. And so if we start with one risk factor, what did I say earlier? Duration sounds like a good place to start. We only have one risk factor. And the question then, how much does this risk factor capture? How much risk of the portfolio does duration capture? And if the answer is 100%, well, then we're stuck with 1, and that's all we need. But if the answer is 5%, well, then we need to add. Now, of course, duration is probably going to capture a large amount. It's not going to be 5%, but it might be 60%, it might be 80%. So then let's add some things. Let's add credit risk to the story, right? Then let's add currency risk to the story. And then let's add something else and something else. And so notice what I say in the bottom, chip away at specific risk even further. So the ultimate end question is, can we ever get rid of that idiosyncratic risk? And of course, that's really an empirical issue for each portfolio. All right, let's take a deep breath and go through the math. I encourage you to stop the video if you need to, replay this. Not that I'm telling you that to go back and rewatch all the stuff that I'm saying, but go slowly so that you can understand the math, so that you can answer some of those questions related to the learning objectives. Now, as we go down that left-hand column, we're going to add an element of precision. So principal mapping is going to be really quite simple. You're going to be shocked at how simple that thing is. Duration matching is really not even that much more complex than principal matching, and then cash flow mapping is fairly complex, and so we're going to have to take a little bit of time on that one. But essentially what we're trying to do is we're going to try to identify what are these important risk factors so that we can come up with a more precise estimate of value at risk. Now, to do that, let me just, at the risk of offending you, go ahead and remind you about the relationship between the duration of a fixed income security and its value. And so that blue equation I have there, the change in P over P, that's going to be the percentage change in price is a function of, in fact, it's equal to a minus duration. And just remember that minus sign is because when interest rates go up, bond prices go down. Reminding us of that negative relationship. So we're going to take the duration, the negative duration, times the change in yield. All right, so notice what I have in the middle block point. The equation tells us that if the yield changes by 1%, then the bond price will change by a certain percentage in the opposite direction, and that certain percentage just depends on duration. So for longer duration bonds, you're going to have a higher price response. That should make perfect sense. But now let's go ahead and apply that to value at risk. So what we want to do is we want to calculate the value at risk of the percentage change in price. We call that the returns value at risk. And that's going to be equal to the duration. And we do the absolute value sign on there because we don't really worry about the negative when we're doing value at risk. So we're going to multiply the duration times the value at risk of the change in yield. And that should make perfect sense. So really all we're adding is that, when duration goes up and then interest rates go up, then the value of the portfolio goes down by a larger amount. This is what we know from our very first days of investments class. Longer duration bonds have greater interest rate risk. And so this is just an equation that illustrates that. All right, let's take a look at an example here for the next couple of slides. Let's suppose we have a portfolio, 2 bonds that are selling at par value. We've got 100 million in bond 1, 100 million in bond 2. We have different we have different coupon rates, 4% and 6%. And we've got a 1-year bond and a 5-year bond. Now let's go ahead and talk about this table, and notice I've got all the headings there, and then the changes are going to be based on a 95% confidence level. Now we've got a 1-year bond and a 5-year bond, but we need to worry about the yield curve in between all those things. So that's why we have maturity and years going down the left-hand column of between 1, 2, 3, 4, and 5 years to maturity. Remember how important all that was when we talked about spot rates and par rates, and we did that a long, long time ago. And then, of course, we need a yield curve. So there's a yield curve, 5.83 down to 5.71, then back up. So this is, kind of an upward sloping yield curve with a beginning dip in it. And then notice in one of those middle columns, the Macaulay duration is 1, 2, 3, 4, and 5. So that must mean that those yields over there, the 5.83 down to the 5.96, those have to be yields on 0 coupon bonds that mature in 1, 2, 3, 4, and 5. All right, there's the yield value at risk. And notice that those all look like they could be 0.5%, right? They're very close to 0.5%. So at the 95% confidence, what we're saying is, let's suppose that we're worried that the yield, value at risk, is that the yields are going to increase by, what is that, around 50 basis points. So we're worried about a yield value at risk of about 50 basis points at each moment in the yield curve. And then that modified duration is going to be less than the Macaulay duration. Let me just quickly remind you of that first one. So take the Macaulay duration of 1, divide it by that first yield of 1 plus that first yield, 1.0583. You get the 0.945. All right, so we're constructing this based on some yield curve that we have and some yield value at risk, which depends on the 95% confidence interval, and then our modified duration. And then all we really need to do is multiply the modified duration column by the yield value at risk to get our price returns value at risk. So let's do that first one. So take 0.497% times 945 modified duration, and you get the 46.97. And of course, the bottom block point, I give you an illustration there. So take the 3778 times the 522, that gives you the 1.9721. So in the event you have to construct this table, you're probably going to be given most of it, right? You have to be given most of these as input variables. What you could calculate is modified duration, you could calculate. But I suspect that if you were to have to calculate anything, it would be that returns value at risk over in the far right column. And remember, those are in percent forms. All right, so this is really just setting the table. We haven't really done anything yet. This is a description of our portfolio, given information that we're used to, right? 6% coupon rate, 5 years to maturity, all that kind of good stuff, duration, but then we're adding this concept of yield value at risk and returns value at risk. All right, so remember I said there are 3 ways to do this mapping. So let's do the principal value at risk. So there's the table again. And notice that highlighted in yellow is the maturity period of 3 years, and then that risk factor over there at 3 years of 148.27. And the way we arrive at that is that since these bonds were selling at par value, right, 100 million and 100 million, we have an equal investment. Our portfolio is worth 200 million. It's an equal weighted portfolio. So what we're saying is that having a $100 million 1-year bond and a $100 million 5-year bond is exactly like having a $100 million 3-year bond and another $100 million 3-year bond. So you get the sense here, principal mapping is really just calculating an average time to maturity. And so notice in the first block point, I have a little formula there. That's really a complex one. We take the 1 plus the 5 divided by 2 to get 3. So there's our risk factor over there, 1.4827%. Multiply that by the $200 million market value of our portfolio, and we have a principal mapping value at risk of, what is that, about 3 million. 3 million. So you get the sense of what we're doing here. We're taking a risk factor, and we're using that to compute the value at risk. Wow, this is illuminating based on all the stuff that we did earlier. What did we do? Historical value at risk and Monte Carlo simulation and all that kind of stuff. So this one is pretty simple, but it's also pretty cool. Now, of course, you should be saying to yourself, all right, Jim, what we know is that we're not really worried about 1 year and 5 years and 3 years. What about the duration? Of course, that modified duration is not going to be, this is not a 3-year duration portfolio. And so that's what we do with duration mapping. And instead of, here, let me go back to this thing. Instead of a 3-year maturity, what we want is a duration matching maturity date, so to speak. I didn't say that very clearly. So notice that first block point. We replace the portfolio by a 0 coupon bond with the maturity equal to the duration of the portfolio. Now, if you go back to the chapter, it took me a couple of times to read it to try to figure out what the author was trying to pull off, but it does work mathematically. I think it's a little bit easier if you just do this. First thing you do is calculate the duration of the portfolio. So this goes back to your very first investments class. So the 5-year bond there, the cash flows, right, a 6% coupon rate. So that's 6 all the way down to 106. The 1-year bond has a 4% coupon rate. So all we're getting is $104 a year from now. There's some spot rates that are given. And those are right out of the chapter, by the way. Take the present value and then sum that present value column. And of course, you shouldn't be surprised to see 200 there, right? We came up with the idea that these bonds were selling at par value. So our portfolio has to sell at par value. But then that last column, and this is how we get the duration of the portfolio, multiply those present values by the time. So 105 times 1, 5.48 times 2, 5.15 times 3. So you get that third column, and then you do the summing down there. And so you're left with 545 divided by 200. That gives us a portfolio duration of 2.726 years. Now, if I were really a cool instructor and a cool professor, when I hit the next arrow button, what I would have down the left-hand column is maturity of 1, 2, and then 2.7267, and then 3, and then 4, and then 5. But unfortunately, what we're called to do is interpolate. And there's one of my favorite math words. And if you go back and look at the reading, the author does this interpolation a really, really interesting way. Why don't you just do it this way? So what do we know? We know that we have between 2 and 3, right? We have those risk factors, 98 and the 148. And so between 2 and 3, 2.72 is really close to 3, right? How close is it? Well, it's 27 out of 30, it's 90% really. So just take 90% of the 148 and you get, well, there it is at the bottom, 1.3474. So multiply that 1.3474% times the 200 million, we get the duration mapping value at risk of about 2.7 million. And so this makes sense, right? Back here with the principal mapping, we got about 3. But that was based on a maturity date of 3 years, right? And a weighted average maturity date. So when we use duration, assuming these are coupon paying bonds, which of course they are, 4% and 6%, we have to get some lower number, right? So this is about 2.7%. What did I say to you just a few moments ago? The principal mapping is really, really easy. The duration mapping is just about as easy. You just have to do some quick math. But it makes more sense then that the duration mapping value at risk captures more of interest rate risk than the principal mapping one. That sounds like a great question to me. All right, how about cash flow mapping? This is where it gets just a little bit confusing because we're going to have to use that big old correlation matrix here. So let's explain this table, and this table is right out of the right in the chapter as well. So left-hand column, we have the years, 1, 2, 3, 4, and 5. And then the next column, those are the present values of the cash flows. So we just did that in the previous slide, right? And then let's go ahead and multiply those present values by the returns value at risk, right? So there are risk factors there on the right column. So 4697, so put that in your calculator. Remember, that's a percent, so do 0.004697 times the 105, and you'll get the, well, whatever that number is, 4968. All right, so those are the, that's the column that multiplies the present values times the price returns value at risk. And then notice I've got the 1 year, 2 year, 3 year, 4 year, 5 year, and then the ones on the diagonal. So that thing in there, that 5x5 matrix, is the correlation matrix between and among the 5 positions. And so note, they're all pretty high, which probably makes some sense. And then I have that last column out there, and I'm going to ask you to ignore that last column for just a second, and I'll come back and explain that last column here in a minute. Now, remember we went back to that William Sharpe thing where we were comparing systematic risk and unsystematic risk. And remember, we said that systematic risk was common to some kind of an index or some kind of a benchmark, right? And so what we're concerned about here is how diversified is our fixed income portfolio? And then if it is not diversified, then how much is it not diversified? All right, so what we're first going to do in this cash flow mapping is we're going to compute an undiversified value at risk. And all we're really doing is summing that third column. So that gives us an undiversified value at risk of 2.633. Excuse me. Which then asks us the question, excuse me. Which then asks us the next question, okay, well, what happens if we have a diversified portfolio? What is the diversified value at risk? So back here, we're worried about undiversified, which is kind of total. And then here, we're worried about diversified. And that's where this right-hand column comes in. We're just going to sum that right-handed column and then take the square root and get the 2.57. So the undiversified value at risk 2.6 and the diversified value at risk is about 2.57. Now, before we go on, what I want to do is take a minute of math and show you how the author got that 2.57. And the answer lies in our ability to understand matrix algebra. And so what I did is I got out my old Excel spreadsheet and I said, all right, I remember this from my graduate school days. All right, so look in the middle. There is our variance covariance matrix, and that's 5 by 5. On the left, I have a row of those risk factors, right? Those are the returns value at risk, the 4968 all the way over to the 191. And then notice over on the far right, I have those same numbers, but they're arranged in a column. So here we have the row, and then here we have the column. And let's suppose that that's a 1 by 5 matrix times a 5 by 5 matrix times a 5 by 1 matrix is going to give us a 1 by 1 matrix. So we're going to get an answer here. And so if you want to play around with Excel, just go in and hit your mmult function. And you have to multiply two matrices at a time. So you're going to do that thing by that thing, and you'll get an answer. Then the resulting answer multiplied by that thing. So here, if we go back to that far right column, the 1.15 all the way down to the 488, that is the resulting matrix in the intermediate. So what we're going to do is just add all those. So let me go back here. When you do all this in Excel, you're going to get, let me go back here, you're going to get 6.6192. Then, since, notice we had that 1 by 5 matrix, and then we multiplied it by the 5 by 1 matrix all the way at the right-hand column, so we're squaring. So we're essentially squaring those risk factors. So, whoops, I went the wrong direction. What do we have to do? We have to take the square root. So make sure you take the square root to get the 2.633 and the 2.57. In summary, we have an undiversified value at risk of 2.63. Now remember, that undiversified value at risk is when those bonds are perfectly correlated. So then we ask the question, what about if they're imperfectly correlated? And that's why we computed the diversified value at risk at 2.57. All right, so let's compare that to, where were we back here? So here's our duration mapping 2.69. Here is our principal mapping 2.96. So remember, I was telling you that as we move through this, we're getting more and more precise. So we start with 2.96 million as our principal value at risk. Then we get down to 2.69 duration mapping value at risk. And now, let me see, I got one more. Now we're going to ask ourselves the question under the cash flow mapping value at risk. Are these bonds in our portfolio, remember there are just two of them, are the bonds in our portfolio, are they perfectly correlated or are they imperfectly correlated? Well, that's why we have the 2.63 million of undiversified value at risk and the 2.57 million in diversified value at risk. So we need to make a judgment here based on whether or not we have accurately calculated those correlation coefficients or if there's some other variable that we need to consider. And so in summary here, again, we're just adding to the precision of our value at risk estimate. Oh boy, so what that does is that summarizes the mathematics behind those three methods. Now, I said this earlier, and I might have said it just briefly, but let me go ahead and emphasize this. We've talked in previous chapters about stress testing and how important it is to stress our models. Well, as you can imagine, this value at risk mapping helps in stress testing. All right, so what we want to do is we want to find out how the portfolio would be effective if each bond in the portfolio were decreased by its unique value at risk. And so the important point here in this stress testing slide is that what's going to happen is that we're going to be able to do this stress testing in a much more precise manner, in a much more efficient manner because of all that stuff that we just did. Now, remember, one of those last learning objectives asks us to compare this to a benchmark. We always do this. We learned this all the way back from William Sharpe in the early 1960s, that we need some kind of a benchmark portfolio. And then we've gone through, however many years ago it's been there, 50 or 60 years. And so what we can do here is we can estimate our tracking error value at risk using that formula there that I have in the middle of the page. There's a good equation. And notice in parentheses, there's the x minus x0. So that's going to be the difference between, our portfolio and the benchmark. And then there's a little dash up there. And then there's the variance covariance matrix. And then there's that same x minus x0. So at the risk of patting myself on the back, let me just go back here and remind you that this is the same thing of what we're doing here with tracking error. We're taking the x minus x0, so that's the dash, which means it's a row, and then x minus x bar without the dash, that means it's a column, and then there's some kind of variance covariance matrix in the middle. And so we're essentially computing that tracking error value at risk, at some confidence level, and we have to take the square root as well. And the last learning objective asks us to do some mapping for derivative securities. And the way to do this is to decompose the derivative. Remember, a derivative is a security whose value is derived from another value, and you can replicate that derivative or the underlying asset with a combination of a host of other financial securities. And so that's what you need to do. You need to break down the derivative into its component securities. And what it does, it makes it more simple. So look at a forward contract. On a currency. So what is this? It's like shorting a treasury. It's like taking the long position in the euro and then a long position in the spot market. So you have those three components, and therefore you can map each one of those. I mean, it's easy to map a treasury bill, right? And it's easy to map an exchange rate. It's easy. So you just sum all those and you get the mapping of a forward contract. And you do the same thing with a forward rate agreement, right? That's the long position in a bond, zero coupon bond with one maturity, and a short position in a bond with a different maturity. I mean, this is how we price forward rate agreements. This is how we price swap contracts. And so you just take those two maps and those two risk factors, and then you sum them. Now, the option is a little different because you take the long position in a stock, and then you have to take the short position in the underlying asset with a margin or some kind of a loan. And then you've got to figure out, what is the delta of the stock? What is the delta, et cetera, et cetera. And then a foreign exchange forward is the equivalent of a long position in a foreign currency bond and then a short position in the domestic currency. And that takes us through those learning objectives. This was a little bit longer time period here than we've been going, but probably worth it.